Okay, so let's get started. Um, let's do a quick recap of what we did in the last class. We started looking at um, what is called the convex combination, right? So we saw what a convex set is, and I also gave some intuition about why you need convex sets, and then we looked at how to make something which is not convex into convex, right? Towards that, we looked at convex combination. What do you mean by convex combination of some k points? And subsequently convex set that converts a non-convex set into a convex set. Then we also looked at what is called the conic hull. Well, I left that as an exercise. So one way of how do you get a conic hull? You just pass, a line from the origin through all the points, and then take the convex hull of it. So that will give you the conic hull, right? As an example, we looked at half spaces. Half spaces turned out to be a convex set. Then we looked at an example wherein, so of course, the intersection of convex set is a convex set. We saw the proof. And then we looked at a specific linear program where the constraint set corresponds to the intersection of half spaces. So it's a convex set. We also, I basically gave some intuition about how to solve linear program, not how to, but what to expect out of a solution from of a linear program. Then we started looking at what is known as convex functions, right? So we characterized what a convex function is. So basically, you take any 2 points, draw a line between the two. All the values on that line will be above the function, right? So we mathematically characterized that. And then we looked at a few consequences of this. One consequence was f of x is greater than or equal to f of I plus x minus y transpose times the gradient of f of I, right? So this is true for any xy in the domain of the function for any convex function. Then we also looked at a few other consequences. For example, if you look at the remainder form of Taylor series and use the consequence of the convex function, it turns out that the Hessian is positive semi-definite, right? So the other way is also true. Maybe we will come back again a little later. So I gave some intuition of how to prove it. You write these two equations. So the inequalities are true. Inequality is true for any convex function. So you basically use that inequality to prove. So what do? So basically, you look at on the left hand side. So the intuition is this, right? So you have f of the linear combination that should be below the line, right? That's what you'll end up doing. Okay. Anyway, so let's get started today. So we looked at a few other functions, right? E power x is convex, minus log of 1 plus x is convex. So that means log of 1 plus x is concave, and so on. That's where we concluded. So we will start. So we'll look at a few more convex functions today, right? So the first result you have to remember is f Rn to R is convex implies, what can you say about the Hessian? What can you say about the Hessian? It's positive semi-definite, right? So, and if a function is positive semi-definite in its domain, then the function is convex. So it's an if and only if. Okay. So how do you verify a function is convex? Let's look at a few examples, maybe. Can you give me an example of a convex function? So let's look at the first example, which is norm. Why, for example, you have a norm in n-dimensional space, is it convex? Well, you look at lambda x plus 1 minus lambda y norm, which is less than or equal to norm of lambda x plus norm of 1 minus lambda y, which is equal to lambda times norm of x plus 1 minus lambda times norm of y. So norm is convex, right? So that is clear. What else? Can you give me a few other examples? Norm is convex, great. What else? That means, remember, sup norm is also convex. That means if you look at n-dimensional vector, look at the max of the absolute values, right? That is the sup norm. So even that is true because of, it follows from triangular inequality again, right? So any other function, not so obvious, but okay. So I won't prove this. Geometric mean is convex. Okay, so I'll leave it as an exercise. You should see what is geometric mean. So can somebody tell me what is geometric mean? Arithmetic mean is the simple average, right? What is the geometric mean? I give n numbers x1 through xn. What is geometric mean? You take the product, right? And then nth root, right? That's what you have, right? So that is called the geometric mean. So you can think of geometric mean as taking a vector x1 through xn and giving me a number, right? It's a function. So I can so this function turns out to be convex. Okay, so now let's look at one more consequence of this convexity. So let's suppose you have a function f Rn to Rn is convex. Then what I'm going to do is I'm going to take 2 points in the domain of the function and pass a line through it. Okay, and look at the value of the function along that line. So how do you write that? Then for xy belonging to Rn, let's assume that Rn is the domain, or I'll specifically write. So domain of f, you take 2 points. F of, what I'm going to do is I'm going to take x and ty, right? T is some scalar, x and y are vectors, x plus ty is another vector. Of course, I am assuming that this x plus ty belongs to the domain, so I'm not going to use some t that will take x plus ty out of the domain of the function. So this is, I will call this as g of t for a fixed xy. So you fix xy, and I'll consider x plus ty. So t is a scalar, by the way, right? Is a convex function. Why is this useful? We will see right immediately after this. So let's see, what do you mean by this? So is a convex function for t belonging to R. Okay, so let's see. I need to prove that this is a convex function, right? So what do you mean by that? You look at lambda t1 plus 1 minus lambda t2. This is a convex combination of 2 points, right? T1, T2, right? Now I have to prove that this is less than or equal to lambda times g of t1 plus 1 minus lambda times g of t2. So let's see what does this mean. So this means f of x plus, so instead of t, I have to put lambda t1 plus 1 minus lambda t2. So what do we get? We get lambda t1 y plus 1 minus lambda t2 y. I'm just multiplying it, that's all. Now x, I can write it as lambda x plus 1 minus lambda x, right? Convex combination of x and x is x itself, right? So this will be f of lambda x plus 1 minus lambda x plus lambda t1y plus 1 minus lambda t2y. Simple algebra. Now what I'm going to do is collect all those with lambda. Lambda times x plus t1y plus 1 minus lambda times x, y plus, this will be x plus t2y, right? Well, the only obviously x plus t1y belongs to the domain of the function. X plus t2y also belongs to the domain of the function. So it's a convex combination, so obviously it should belong to the domain, right? So now I'll use the convexity of f, right? F is convex. I'm taking 2 points, 2 vectors, x plus t1y, x plus t2y and taking the convex combination. So this should be true, right? So lambda times t1y plus 1 minus lambda times f of x plus t2y. Okay. So now this is lambda times, see what is f of x plus t1y? G of t1, right? It comes from here, right? So g of t1 plus 1 minus lambda g of t2. Okay. Now, if I ask you to prove that a function is convex, or if you have to verify that a function is convex, the first thing that you do is first principle, right? Take 2 points, convex combination less than or equal to. You try to prove that. Or you can take the Hessian and prove that it's positive semi-definite. Or you take 2 points, any 2 points, pass a line and show that g of t is convex, right? There's so many ways. Let's see how to use that. This is a very nice exercise in optimization, or in general proving convexity using some linear algebra that we have studied. Okay, so okay, it's fine. So let's look at an example now. Okay, let x belongs to Sn plus. It's a positive semi-definite symmetric matrix. Okay, fine. Then the function log of determinant of identity plus x, what does it do? It takes x as input. X should be in Sn, so basically it maps Sn plus n to, what does it map to? Can somebody tell me? It gives me a number. What kind of numbers it will give you? Huh? Can it be 0? So log det of something can be 0. Yes, right? When determinant is 1, it will be 0. When will it be 1? It should be identity. When will it be identity? X should be 0. So if you take 0 matrix as input, this function will give me 0, right? Can it be negative? Huh? Fractional values, right? So that means if I take identity plus x determinant to be fraction, then can it happen? Can you get fractional values? See, x is positive semi-definite. Okay, the eigenvalues are always non-negative. Now, can you get a fractional value? Not really, right? All the eigenvalues, if x has eigenvalue lambda, right? One of the eigenvalues is lambda. What will be the eigenvalue of I plus x? One of the eigenvalue will be 1 plus lambda, right? So it will be always greater than 1 because lambda is non-negative, right? Therefore, it will be taking the product. Log of determinant of x is product of the eigenvalues. Log of determinant of identity plus x is product of 1 plus the eigenvalues, right? So it will be at least 0, I mean, it will be above 0, right? So it should map to R plus. So this is a function, right? So this function is convex. Well, how do you prove this? This is convex. One way is, you take two matrices x1, x2, take lambda x1 plus 1 minus lambda x2 and do all that, right? Let's look at a simpler proof, which is, let's use the line passing through 2 points, right? Let xy belongs to s plus n and t belongs to r. Okay, this is what I have to do, right? Of course, if x and y are positive semi-definite, x plus ty will also be positive semi-definite, so I don't need to worry, right? So now let's look at, you consider g of t, right? What is g of t? What is g of t? This is log of det of identity plus x plus ty, right? This is what you have. Fine. So now I want to prove that this as for a fixed xy, this as a function of t is convex, right? That's all I have to prove. So let's see how to prove this. So any idea how do you prove this? What is it that you will do? Any idea how you prove this? So how do you prove that this as a function of t is convex? So what kind of manipulation you will do? Hmm? What are the things that you can do? Okay, so what I'm going to do, let's try these things. Okay, so I'll take I plus x outside, right? Identity plus x is always invertible. Why? Can somebody prove that identity plus x is invertible? See, identity plus x, I can write it as identity plus. So what kind of matrix is x? X is positive, semi-definite, symmetric. So the moment I say positive, semi-definite, symmetric, what comes to your mind? Apart from symmetric and positive, semi-definite, obviously. But what else? Huh? Of course, that's what you mean by positive semi-definite, right? Huh? Eigenvalue decomposition, right? So we can always do eigenvalue decomposition, right? So now I can write it as UU transpose for identity. So I'll take U to the left. This will be identity plus lambda, U to the right. Okay. Now what is the inverse of this matrix? Maybe I'll write this as an aside. What is the inverse of this matrix? So you have U identity plus lambda times U transpose. So I have to multiply it by U to cancel U transpose, right? U transpose U is identity. Identity plus lambda is a diagonal matrix with diagonal entries being equal to some value greater than 1, right? So it is invertible. So I can do inverse, right? U transpose. This is your inverse. So this matrix is invertible. So I plus x is invertible. And I know the inverse also, right? So what I'm going to do is I'm going to take the inverse out, or I plus x out, okay? So I'm going to take identity plus x out. What do I get? I get identity here, right? In the place of identity plus x, because I have pulled it out. Then what do we have here? We have t times y, right? If I pull a matrix out, A plus B, if I pull A out, what would we get? Identity plus A inverse B, right? Yeah. So I should get t times identity plus x inverse y. Do you agree with this, everyone? See, I have log det of identity plus x times something. What is determinant of AB? What is determinant of A times B? Product of determinant of product of matrices is product of determinants, right? Determinant of AB is determinant of A times determinant of B. So I can use that, but I have a log outside. So log of product is sum of logs, right? So I'll have this plus, what is the next term? Next term is this identity plus t times identity plus x inverse y. Okay. What is the next step? If identity plus x is a positive semi-definite matrix, obviously, right? X is positive semi-definite, y is positive semi-definite. Sum of positive definite matrices will always be positive definite. In fact, it is positive definite symmetric, right? So what can you say about inverse? We already saw, right? Identity plus x is basically this, right? Inverse is basically this. This is definitely symmetric, right? If you take the whole transpose, U transpose becomes U. I plus lambda whole inverse transpose is I plus lambda whole inverse only. And then U becomes U transpose. So it's symmetric, right? Okay. So now I plus x whole inverse is symmetric. Y is symmetric and positive semi-definite, right? So what do you think is the next step? So what should I do? Any idea? Hmm? What should I do? Any what do you think is the next step? Hmm? What should I do? What should I do? Yeah, come on. Any idea here? So what is it that I have to do? So now basically I have to prove that this matrix, this as a function. So this I can ignore now, right? So we can basically can ignore this, right? Because it's independent of t. So I take a convex function, add a constant to it, it will still be convex, right? So it doesn't matter. Now as a function of t, I have to prove that this is invertible, right? Sorry, it's convex, right? Now suppose, for example, this is suppose, okay? You should verify and tell me whether this suppose is true in the next class. If suppose is not true, then we need to think. But suppose I plus x whole inverse y, the product has an eigenvalue decomposition. When I say has an eigenvalue decomposition, I mean u lambda u transpose kind of a decomposition. So if it has an eigenvalue decomposition, what do you get? The first term as is, right, plus log of determinant of identity plus t times, I can write this as something like v, what happened, v sigma v transpose, right? You agree? Now the usual stuff, right? Plus log of determinant of identity plus, well, now what happens? I can pull this v out here, this v transpose here. Do you agree? VV transpose is anyway identity, so I can write this as VV transpose. So I pull the one V to the left and the other V to the V transpose to the right. So what do I get? Log of, why is this true? Because determinant of V times something diagonal times V transpose. So V transpose, determinant of AB is determinant of BN. So V transpose will go to the other side and it cancels, right? We saw that as an exercise when we studied linear algebra. So VV transpose will be identity. What we get is determinant of identity plus T times sigma. Now what is the next step? Well, identity plus T times sigma is basically diagonal, right? So determinant of the diagonal is product. So log of the product is sum. Let's say it's an n-dimensional or n cross n matrix, it will be log of 1 plus t times lambda. Okay. Now what is log of 1 plus t lambda? Well, I think I made a mistake. Then the function is, I'll put a question mark. Let's see what the function is. Okay, so sorry about that. It's not convex. We'll see what this is. What is log of 1 plus t lambda? What kind of a function is that? Can you please check quickly and tell me? Lambda is or positive? Okay, so this is, what kind of a function is log of 1 plus ax as a function of x? How do you check whether it's convex or not? What do you do first thing? Well, you can take the second derivative, right? And see if it's positive, non-negative. So how do you prove that? How do you see that? You take the first derivative. First derivative is 1 over 1 plus t lambda I. What is the second derivative? Minus something over 1 plus lambda I ti whole square. Lambda I t whole square. So it's negative, right? So that means minus of this is convex. So what is log of 1 plus t lambda I? Concave. So that means for each I, this function is concave. What is if you have f1 is concave, f2 is or let's say f1 is convex, f2 is convex. What can you say about f1 plus f2? Convex, right? Why is that? Is that true? Did we verify that? No? Okay, let's verify that. Okay, so if f1 and f2, or for a change I'll say concave, then f1 plus f2 is also concave. I want you to verify. It's a trivial exercise, but of course, if it's true for 2, it's true for 100 billion also, right? Induction. So this implies that log of determinant of identity plus x is a concave function, okay, because it's negative, right? Sum of concave functions, concave function. So let me just write this. So instead of question mark, we have concave. Okay, concave looks like this, convex looks like the downward. This is a nice thing to look at, right? So let's go back and see what is it that we did. So essentially, we looked at one way was we took identity plus as common, and then t times y times identity plus x whole inverse is what we got, and then we assume that this is decomposable, and therefore we proceeded and we got this, right? That's what you get. Is that fine? Okay. Okay, another question. So anyway, you have to think about this. If it's a question in linear algebra, okay. Okay, I'll say belong to implies AB belongs to this. Not really, or no, or yes. Okay, let's not. Okay, symmetry is too much to ask for. Let's say it's positive semi-definite. Implies AB is positive semi-definite? Question. If so, you should prove. If not, you should give a counter example. Okay. Yeah. Okay. Anyway, so let's revisit this. Okay. So keep these questions in mind. In the next class, we will discuss and see if it's true. Okay. Yeah. So at least we saw a few examples. Let's look at one more example of a convex or a concave function. So the function looks like this. Okay. Okay, maybe you can add one more number c. Okay. So this is what kind of a function is this? Okay, x transpose ax. What kind of a function is that? Okay, so let's give me some. I'll just tell you one small thing. X squared plus bxy plus cy squared. Right? What kind of a function is this? It's quadratic, right? In xy, right? I can write this in a different way, right? So xy something times xy. Do you agree? Now I can fill something here, some numbers, so that when I take the product, I'll get this. Now my question is, again, it's a homework problem. You should figure out what numbers I have to fill so that I get this. How do you do that? Well, you call this as some C1, C2, C3, C4 or something like that, and then multiply this explicitly. You'll get an expression, coefficient by coefficient, you map. Right? That will give me what C1, C2, C3, C4 are. Right? It's the easy thing. Okay. So I can think of this as a vector V transpose. This as vector V. So it's V transpose some matrix times V, right? It's called quadratic. So this is also a quadratic function, right? In general, if I write x transpose Px or x transpose Ax, it's quadratic. Now we have a quadratic function. So is this convex? Obviously not, right? Quadratic is, in general, it could be like this also, right? Can it be like this? Huh? Any idea? How do you show that this is convex? What is it that you have to do? You have to take the second derivative. In this case, Hessian, right? What is Hessian? First derivative is what? X transpose Px. Well, matrix derivative you may not know, or vector derivative. So let's use intuition, or you can just download the matrix cookbook or whatever, the derivative cookbook, couple of pages of these kind of results which you can use. So what is the derivative of, let's say, Px squared? In one dimension, it will be Px squared, right? What is the second derivative of Px squared? Come on. What is Ax squared derivative, second derivative? 2a, right? Right? So you have x transpose, it's like x times p times x. What will be the second derivative? It's 2 times p. right? So this derivative, the Hessian of this will be 2 times p. Of course, we have a half there, so 2 cancels, we have p. And then b transpose x, it's linear in x. So if I take the second derivative, what do I get? 0. Constant anyway, 0. So I get p. So now, if it has to be convex, then this is what you need to have, right? It should be positive semi-definite. So if the matrix P is positive semi-definite, the quadratic function will be convex. On the other hand, if it is implies F convex. On the other hand, if it is negative semi-definite, it's concave. That's all. What happens if it is equal to 0? I mean, meaning it's equal to 0, meaning it's a line, right? You will only have b transpose x. What kind of a function is b transpose x? It's a straight line, right? Hyperplane. Hyperplane is what? Convex, concave? It's both, right? Both concave and convex, right? Okay, is this clear, everyone? Got it? So you have the convex function now, right? So now let's, I think we should soon get into the algorithms, right? That's what you will actually write in your, let's say if you look at your, how many of you have used TensorFlow or something like that? It's okay, I won't ask any tough questions or anything, don't worry. Have you used TensorFlow for neural networks, right? No? Okay. Of course, the way you fit a model is there is something called model.fit, right? So it'll do everything for you, right? A high school student can do it, right? But what goes behind that is what we should understand, right? As engineers. So there is something. So when you do model.fit, you should also tell how you are going to optimize your neural network. What do you mean by that? What kind of an algorithm I'm going to use? So you pass what is known as SGD, right? Stochastic gradient descent, right? Well, let's for a moment, don't worry about stochastic. Let's only look at gradient descent, right? Let's understand gradient descent. That is good enough to understand stochastic gradient descent. All that you have to do is, you take a course in probability theory and to figure out how to handle that small random fluctuations. But otherwise, it's gradient descent only. Okay, let's see. In order to understand that, first of all, we will look at a few things, right? So in the last class, we looked at what do you mean by strictly convex and convex, right? Instead of greater than or equal to, you have greater, it will be strictly convex. Okay. So now let's see if it is strictly convex, whether you will have a single minima or global minima or multiple global minimas, right? Let's look at that. Okay, fine. So let me write it as a theorem. Let's try and see if we can prove it. I'll do it for maybe I'll do it for a general case. Rn to R be a strictly convex function. Strictly convex function. Then there exists a unique global minima. Okay, there exists a unique global minima. How do you prove this? See, essentially, I'm saying the function looks like this. This is how it looks like, but not like this, right? This can never happen, right? Well, nor this can never happen. Both are at the same level, right? So how do you prove that this is true? What is your, I think, so next class is philosophy or previous what? You have philosophy class today? So how do you argue out, right? This is true. That's where logic originated, right? Ancient times. So, right. So how do you argue out that you cannot have two global minimas when it's strictly convex? Any thoughts? How do you argue out? First of all, it's very intuitive, right? If you have strictly convex, you should have only one global minima, and you go in the direction of the descent, you can reach the global minima. All that is great, but If that is what you want, then PUC is enough, right? So that will tell you. But how do you know that that is true in some 100 billion dimensional space, right? Or 10 million dimensional space, which is not at all impractical, right? Nowadays you have deep neural network with 10,000, 10 million, or even 10 million coefficients, right? If you have 10 million coefficients, it's 10 million dimensional space that you are looking at, right? F of x1, x2, x3, and so on, x 10 million, right? That's the dimension. So you're optimizing such a function. So now, how do you know that things won't be like this? So how do you prove this? What is the first thing that you? I mean, if you see this kind of mathematical problem, what is the logically? What is the first thing that comes to your mind? Huh? How will you prove that there cannot be more than one? Huh? Explicitly show somehow, right? You look at all possible functions and say, well, none of these have two minimas. Otherwise, proof by, okay, huh? Huh? Sorry, can you repeat what? Contradiction, right? So you can prove by contradiction. So what do you mean by contradiction? You assume that there are two, right? Or multiple, but two is enough, right? If you can prove for two, you can prove for multiple. So that's what we will see. We will try to see if we can prove. Okay. Suppose you have two values, xy belonging to domain of f, or two minimas, okay, that is f of x equal to f of y, and f of x is less than f of z for all z in the domain, or let's say all z not equal to x, z not equal to y. That means I'm taking 2 points x and y, the function values are same, and one is less than, so you take any other point, f of this is the lowest points, right? So it's fine. Okay, now how do you argue out that this cannot happen? You basically show that, see, we start with a convex function, okay, strictly convex function. You have to prove this. If it's strictly convex, what is the trick? I use a convex combination somewhere here, right? Right? I use some convex combination and do show something, right? All right, is that fine? Or okay, there is another picture that I can write. This is also fine, right? Something like this. Well, not really like this. Something like this. You cannot have these kind of things also, right? This should be unique minima, right? So how do you find, what do you do? Huh? So I take convex combination of x and y, right? So then f of lambda x plus 1 minus lambda y is definitely, remember this is important, strictly less than, it's a strict convexity, lambda f of x plus 1 minus lambda f of y. You agree? But what is f of x and f of y? What is the relationship? Equal, right? Lambda f of x plus 1 minus lambda f of x is what? Of x. So this is definitely not equal to x or y if lambda is not equal to 0 or lambda not equal to 1. So I'll pick lambda equal to half, for example, okay, or not equal to 0 for it's not equal to 0 x or y if lambda is half, for example. It's x plus y by 2. X plus y by 2 can never be equal to x or y, right? So that means I'm coming up with a point, right? That is whose function value at that point is smaller than x. But what did we assume? We assume that x is the global minimizer, right? But I'm coming up with another point which is much better than, right? It's almost like saying, okay, there are two neural networks which will work really well for a convex function or loss and everything is convex. Then what I'm saying, I'm going to come up with a new neural network which is much better than both. But what is the assumption? Those two are the best neural network, right? So I'm contradicting the assumption that those two neural networks are the best, right? There can only be one, right? So a contradiction. right? Done. Nice proof, right? Simple, straight, obvious. Okay. Now we can move on to the algorithm. Now we are clear that if it is strictly convex, it looks like this. Now, how do you come up with some kind of an algorithm that takes you to the bottom, right here? Why do you need that? Well, in neural network kind of applications, we saw that, right? We need to minimize the loss. That means I want my loss to be as small as possible. That means I have to go to the deep valley and be there, right? So how do you move into that deep valley? So let's start with that. Let f r into r be a convex function. Then, well, I can also say strictly, okay? Well, not really. I can just stick to convex because strictly I'll go to the global optima, global unique minima. If it is not strictly, I'll go to the minima, right? It need not be global, like a bucket, right? You can pick any point. All that I care about is, I want to go to one of those points, right? So I don't care about, I have to reach the bottom of the bucket, right? So I don't care where. Okay. Then, how do you solve this problem? Okay, minimize overall x f of x. Of course, this x belongs to. This is called an unconstrained optimization problem. Optimization. So, in many of the machine learning applications, especially involving neural networks, mostly it will be unconstrained. Even if you regularize, it will be unconstrained. Okay, so all that we care about is solving unconstrained optimization problem. But if you look at data analysis in general, of course, there are many problems where you have constraints as well. Okay, so at least we will start with this. If you can solve this, maybe you can solve the bigger problem as well. Okay, so now what is the solution, right? What is the solution? You take the gradient, equate it to 0 and find the point, right? Derivative equated to 0, find x. Strictly convex, you will get a unique minima, right? That's how you do it. But finding the gradient equation can be very, very complicated, right? For example, some e power x plus minus log of 1 plus x, right? So very complicated function. Maybe you can solve, I don't know. Yeah, you cannot solve. It's like a complex function, right? So how do you solve? You come up with an algorithm, right? So what is that algorithm? It's called gradient descent, right? How many of you have heard of or already studied gradient descent? Can you please raise your hand? All of you? Yes or no? All. What about others? No? Which course did you study gradient descent? A course taught here or PRML? Okay, what did you study in PRML? So you studied gradient descent, but what else in gradient descent? Okay, forget about stochasticity. So what else did you study? Did you study convergence? No. Okay, good. At least have some story to say, right? So let's start with gradient descent. Moving forward, I'll call it as GD for short. Okay, so I'll use GD. Now, what is a gradient descent? So how do you write the algorithm, right? So this is how you typically write the algorithm, right? So it's gradient descent. Okay, so what do? You run this algorithm t times. So essentially, input x0 belong to domain of f. So you take the initial point. So what do? I run a loop, right? For t equal to 0, 1, etc. I'll run till t, capital T, and I'll stop after that. So you do what? You do, maybe okay, t is fine. I'll update the point as follows, is equal to xt minus eta times the gradient of the function at xt. That's all, at return If you do it t times, return xt plus 1. Okay. Or I think let me x0 is fine. I think x0 is fine. Okay, fine. Now, geometrically, what is it that we are doing? Is this clear from the diagram? So this is what you are doing, right? You take some point x naught in the domain. You are going to find the gradient of that at that point. So this will be the gradient, right? Now I'm going to move an eta distance in the direction of the gradient. So if I take the gradient, what will you get? You either get positive or negative, right? Here, what is the gradient? Huh? Positive or negative? It's negative. So if I just add the gradient, I will move in this direction. Do I want that? No, right? I want to subtract. So that's why you have minus here. Minus eta times gradient. So I'll move in this direction. So I'll take what is this point, right? So this is x1. Again, find the gradient, right? It's negative. Negative of negative is positive. You move some distance here and keep on moving. After t times, you stop, right? This is the algorithm. But now, what are the questions? Suppose you came up with this algorithm several hundred years ago. What is the first question that you will ask? Huh? Of course, now you just program and see if it works. If it works, you'll say, I don't care, right? That's how, I mean, that's how we approach the problem nowadays. But what are the other interesting questions you can ask? Huh? Okay, so when and where to stop, that means how do you choose T, capital T, right? Okay, that's one question. So when do you stop, or what should be T? And then, sorry, beyond? No, you should be louder, man. You have the mask and. So what you are saying is, well, instead of stopping here, you go here, right? Well, that can happen, right? So you go here, then it's negative, then you go here, then it's positive, you go keep on oscillating, right? Well, when will this happen, oscillation? When eta is fixed, right, it will keep oscillating. If t is infinity, capital T is infinity, it will keep oscillating. So how do you avoid oscillation? You decrease eta with time, right, with the iteration also. So you'll take smaller and smaller step. It doesn't oscillate like this. It oscillates like this, slower and slower and slower, right? That's how it happens. Anyway, that is one thing. How do you choose eta? What else? First of all, whether you can stop. I mean, eventually it will go to the minima, right? That is another question. If so, how fast? Right? If you want to be epsilon close to the minima, how many steps should I take? So these are many questions that you can ask, right? So let's try to answer some of them. And in doing so, we will look at some of the very, very interesting, we'll make some interesting observations, and we will see some interesting mathematical quantities, which will be very, very useful, even if you look at deep neural networks and ask why deep neural network works, right? Do you know why it works, by the way? For those who have taken PRML, do you know why it works? It works, probably would have run it on many data points, and it works many a times. It works really well if you have deep neural network, but it's not very well understood. People have understood a little bit now. I mean, they have some understanding, but back then, it was not very well understood, right? So some of these inequalities are very, very so useful that it will actually explain why it works. Okay, let's look at the analysis, right? So let's probably start the analysis and maybe continue in the next class. So what is it that I have to prove? I have to prove that if I do gradient descent, right, I will eventually converge. That's the point, right? So let's see proof of convergence. So I'll write this as a heading, and then in the next class, maybe we will write the statement of the theorem, right? Convergence of gradient descent. So what is it that I have to do? So when I say convergence, basically I should see what is f of xt plus 1 compared to f of xt, right? If I see the improvement, if the improvement is, there is always an improvement, and the amount of improvement goes down, well, that's a sequence which is like Cauchy or going down, and it will eventually hopefully go down to zero, right? So that's what we need to see, right? But in other words, I need to check what is f of xt plus 1 minus f of xt improvement, right? So I have to write an equation that relates these two, right? So let's look at this. So f of xt plus 1, and I have f of xt here. So what is the relationship? Can somebody tell me? Huh? It won't be equal, right? If it is equal, then you stop at 0 itself, x0 itself, right? So what is the relationship? So f is convex. The moment I say convex, what is it that you will write? Huh? Okay, so can we say something more? Okay, so before this, let's also make an important assumption. Assume the Hessian of f of x. So if it is convex, what is Hessian of f of x? It's greater than or equal to 0, right? If it is strictly convex, it's greater than 0, right? I mean, nowhere it can be, right? What other? So suppose I say that this is greater than or equal to some lambda times identity. Do you know what this means? What do you mean by a greater than or equal to b? It means a minus b is greater than or equal to 0, right? Right. Similarly here, what I mean by this is I take this matrix, I subtract lambda times identity, I get another matrix. This matrix is positive semi-definite. That's what it means. Fine. Okay. Fine. So now let's write this. So this is equal to this plus, I can do remainder form of Taylor series, xt plus 1 minus xt transpose times the gradient of f at xt plus 1 by 2 times xt plus 1 minus xt transpose the gradient of f at some x star, sorry, Hessian, right, not gradient, times xt plus 1 minus xt, right? What does that mean? Okay, so now let's look at an aside here. Okay, so a greater than b. What does this mean? This means a minus b is greater than 0. What does this mean? This means you take any x transpose a minus b, x is greater than or equal to 0, right? This means x transpose ax minus x transpose bx is greater than or equal to 0. This means x transpose ax is greater than or equal to x transpose bx. Do you agree? This is true for every x, right? This is what we have. Now, what do we have from here? Well, I can think of this as x. It's x transpose some matrix times x. But this matrix is greater than or equal to lambda I, right? I can think of this as A matrix, this as some x. So x transpose AX is always greater than or equal to x transpose BX. What is x transpose BX? Lambda times identity, right? So I can replace Hessian by lambda times identity. What do we get? Greater than or equal to, right? F of xt transpose, I have lambda, okay, this is gradient, right? Plus half times xt plus 1 minus xt transpose. So A will be identity, right? It will be lambda times identity. So what will happen? Lambda will come out. Identity times xt plus 1 is xt plus 1 minus xt, right? Clear? I can replace it by this. Okay. So this will be equal to what? F of xt plus 1 plus xt plus 1 minus xt transpose gradient of f of xt plus lambda by 2 times xt plus 1 minus xt whole transpose times xt plus 1 minus xt is what? Norm of xt plus 1 minus xt. This will be, what is that? Lambda by 2, right? Okay. Now things are nice. What is xt plus 1? So I'm using gradient descent, right? What is xt plus 1? It's xt minus eta times the gradient. So what is xt plus 1 minus xt? It's minus eta times the gradient, right? You agree? So I'll write GD. It follows from gradient descent, right? Plus, okay, this will be minus eta times the gradient of f of xt. Gradient of f of xt transpose times gradient of f of xt is norm of this squared, right? Plus lambda by 2. What will happen to xt plus 1 minus xt? It's minus eta times the gradient. So eta will come out. So we'll have eta squared. Again, this will be, right? So now everything will follow through, right? So you have xt plus 1 minus, of course, eta will come out. 1 minus lambda eta by 2 times the gradient of f of xt squared, right? Is that fine? Okay. So now I can write this in a slightly different fashion. So I can take, so what we have here, it's greater than or equal to, right? I can reshuffle, and so, okay, so what next is, maybe we'll look at it in the next class, okay? So now, essentially it says, so we have f of xt plus 1 here is greater than or equal to this, right? So the difference between these, did I make a mistake? Wow, nobody corrected me. So f of xt, right? It should be xt. xt. So the difference is lower bounded by some constant times the gradient norm squared, right? What is the size of your gradient? How steep the function is at that point, right? Obviously, right? If you have a point and it's very steep at that point, I jump a lot, right? Otherwise, I jump a little, right? So that's how I will go down, right? So we will use this to prove that eventually you will go to a place where it's very close to the optima after so many rounds. How many rounds is something we will characterize. Okay. With this, I'll stop here. Go through this math. We will see various versions of it and various, we look at it from different viewpoints. Okay. With this, I'll stop. Thanks.